In this video, we're going to cover the definition of Bronsted and Lowry acids and bases, and look at the reactions of acids and bases in general terms. We're going to look at the equations for calculating the pH, so we'll convert between the concentration of hydrogen ions into pH and vice versa. We're also going to calculate the pH of a solution of a strong acid. We'll look at monoprotic and diprotic acids. We'll then use Kw to calculate the pH of a strong base. We'll then look at what the acid dissociation constant is. We'll construct expressions for Ka, and we will use this to perform calculations relating to the pH of a weak acid and linking it to the concentration of the acid. We'll then look at how we can convert Ka into pKa, the logarithmic acid dissociation constant. We'll look at what titration curves are, and we'll sketch and explain the shapes of 4 common pH curves you'll come across, and we'll then use pH curves to do titration calculations. Finally, we'll explain what a buffer solution is, we'll look at how you can make both acidic and basic buffer solutions, and then calculate the pH of acidic buffers. For this topic, we need to know what the definitions of the acids and bases are. When we talk about acids and bases in this topic, we're referring to Bronsted-Lowry acids and Bronsted-Lowry bases. You can also have things called Lewis acids and bases, which are not covered in this topic. So a Bronsted-Lowry acid is one which is a H+, a hydrogen ion, or a proton donor. It releases H+ when it's in solution. So this equation shows how a general acid, Ha, when it reacts with water, forms a hydroxonium ion, H3O+. Likewise, a Bronsted-Lowry base is a proton or a hydrogen ion acceptor. So similar to the acid, it will accept a H+ when it's in solution. Again, this is a general equation to illustrate how when a base is in solution, it can remove a hydrogen ion from the water to form BH+. Acids and bases dissociate in water, so this means they break apart into their constituent ions when they're dissolved in a solution. Strong acids and bases will completely dissociate. This means that pretty much every acid or base molecule will split apart into the H+ or the OH- and whatever the other ion is. Weak acids and weak bases only partially dissociate. They form an equilibrium with their salt. The equilibrium will usually lie quite far in the direction of the acid or the base, so not very much H+ or OH- will be liberated. So for example, hydrochloric acid is a strong acid. We can see from the equation that all of the HCl has dissociated into H+ ions and Cl- ions. Sodium hydroxide is a strong base. We can see, like with the acid, it has completely dissociated into sodium ions and hydroxide ions. Ethanoic acid is a weak acid, which is why it's in equilibrium with the ethanoate ion and the hydrogen ion. The equilibrium will lie quite far to the left. Not very much H+ will be released, not much dissociation has occurred. Likewise, ammonia is a weak base. It will accept some hydrogen ions, but again the equilibrium will lie quite far to the left. It's worth noting that acids will only donate their protons when there is a base there to accept them. This is a general equation illustrating what happens when an acid reacts with a base. The Ha, the general acid, and B, the general base, will form the base with a hydrogen, now positive overall, the A-, showing the ion which was attached to the proton in the reactants. We use the word hydrogen ions and protons interchangeably when talking about acids and bases. This reaction is in equilibrium, so it's worth noting that if we add more of the acid or the base, the HA or the B, the equilibrium will shift to the right to counteract that change. Likewise, if we add any more of the BH plus or the A minus, this would cause the equilibrium to shift to the left to counteract that change. Before we can start to calculate the pH, we need to recap what the pH scale is. So it's a measure of the concentration of hydrogen ions in a solution. Even though we think of acids as being H plus ions and a base as being an OH minus or an alkali, the pH scale just measures how many hydrogen ions they are in a given solution. So all the calculations are going to focus around H plus. The pH scale is a logarithmic scale. For example, if we were to go from pH 4 to pH 3, that would represent a tenfold increase in the concentration of hydrogen ions. Likewise, going from pH 7 down to pH 5 would represent a 100-fold increase. Like you saw in the equilibrium topic, we can use the square brackets around a chemical to represent the concentration of it. We'll use this notation throughout this video. The first equation you need to learn and remember is pH equals minus log to the base 10 of the hydrogen ion concentration. Now, using the rule of logs, you could work out the reverse, so you could work out how to calculate the concentration of hydrogen ions, or you can just learn this equation. You won't be asked to show the derivation of it in the exam. So the concentration of hydrogen ions equals 10 to the power of negative pH. We're now going to look at some worked examples. So the first question is a solution of hydrochloric acid has a hydrogen ion concentration of 0.025 moles per decimeter cubed. What is the pH of the solution? So in order to answer this question, the first thing we need to know is what is the equation for determining the pH? So we've just looked at this, and the equation is pH equals minus log to the base 10 of the hydrogen ion concentration. The next step is to sub in the value given in the equation. So we'll write the concentration of H plus as 0.025. And all that's left now is to put that into our calculator and come out with the final answer. It's standard practice to give the pH to 2 decimal places unless the exam question asks you to give it to a different degree of accuracy. So our final answer is that the pH equals 1.60. It's also really important to make sure you set out your answers clearly so the examiner can see you're working out. This could be a question you might get at the start of an exam paper, but it's more likely to be a part of a question worth 6 to 9 marks. So by setting your calculations out in a very logical way, including the equation that you're using, it makes your thought process clear, so should you make a mistake, the examiner can follow the rest of your workings out so you can gain method marks. So the second worked example is a solution of sulfuric acid has a pH of 1.35. What is the hydrogen ion concentration of this solution? So again, the first step is to write out the equation which links pH to hydrogen ion concentration. Since we need to find the concentration of hydrogen ions, we're going to use the equation H plus equals 10 to the power of minus pH. The next step is to sub in the value, so we're going to rewrite this equation, but rather than writing pH, we're going to write 1.35. All that's left to do now is to put this in our calculator and to come out with the final answer. Again, we're going to make sure that we give our answer to an appropriate degree of accuracy, so we can say that the concentration of hydrogen ions is equal to 0.030 moles per decimeter cubed. So we've looked in general terms how to calculate pH from a H plus concentration and vice versa, but what we now need to look is the different scenarios where we can calculate the pH of different kinds of acids and bases. So to start off with, we're going to look at how to calculate the pH of strong monoprotic acids. Monoprotic means that each molecule of acid will release one hydrogen ion when it dissociates. So an example of this is hydrochloric acid, HCl, because it has one hydrogen ion in the acid molecule. If you want to double check, you can write out the dissociation equation and see there is one H plus there. Nitric acid is another example of a monoprotic acid. It's also a strong acid. This therefore means that 1 mole of the acid will produce 1 mole of H plus ions. So therefore we can say the concentration of H plus is equal to the concentration of HA, the concentration of the acid. In this example, we need to calculate the pH of a 0.075 moles per decimeter cubed sample of nitric acid. Nitric acid is a strong acid, so therefore the concentration of the hydrogen ions will equal the concentration of the acid. So the concentration of H plus will be 0.075. We then need to write the equation linking the concentration of hydrogen ions with the pH. Once we've got this equation down, the next thing we need to do is sub in the value of the hydrogen ion concentration. Finally, we just need to put this in our calculator to come up with the final answer. As before, it's best to give our answer of a pH to 2 decimal places, so our final answer is 1.12. This time we're almost doing the reverse process, so we've been given the pH of hydrochloric acid as 2.25, and we need to find the concentration. We know that hydrochloric acid is a strong acid, so the concentration of hydrogen ions will equal the concentration of the acid. We then need to write down the equation linking the pH with the concentration of hydrogen ions. Once we've got the pH equation written down, so the concentration of hydrogen ions equals 10 to the power of minus pH, we need to sub in the value. Finally, we need to put this in our calculator and then give our answer to a suitable degree of accuracy. This means that the concentration of hydrogen ions is 5.6 times 10 to the minus 3, so therefore the concentration of the acid will be 5.6 times 10 to the minus 3. We're now going to look at how to calculate the pH of strong diprotic acids. A diprotic acid is where each molecule of that acid will release 2 hydrogen ions when it dissociates. An example of this is sulfuric acid, H2SO4. So we can see from the equation that 2 hydrogen ions are released when it dissociates. So since 1 mole of the acid will produce 2 moles of the hydrogen ions, this means that the concentration of the hydrogen ions is equal to twice that of the acid. So for example, if we had 0.1 moles of the acid, that means we must have 0.2 moles of hydrogen ions. We can do diprotic acids just the same as monoprotic acids, just being careful to take into account the ratio of the acid to the hydrogen ions that we looked at a moment ago. So for this question, we need to calculate the pH of a 0.2 mole per decimeter cube sample of sulfuric acid. Sulfuric acid is a strong diprotic acid, therefore the concentration of the hydrogen ions will be equal to twice that of the concentration of the acid. We then need to make sure we've got an equation down linking pH to the concentration of H+. We also need to work out what the concentration of the H plus ions are. So in this case, we've only got the concentration of the acid. So we can use the equation we've just written to work out the concentration of the hydrogen ions. So we've now worked out that the concentration of the hydrogen ions is 2 times the concentration of the acid, so 2 times 0.2, to give us a concentration of 0.4. We know that pH equals minus log to the base 10 of the concentration of hydrogen ions, so all we need to do now is sub our concentration of hydrogen ions into that equation. Therefore, pH will equal minus log to the base 10 of 0.4, giving us a final answer of 0.4. We can also calculate the concentration from a pH. So for example, we can calculate the concentration of sulfuric acid with a pH of 1.3. So again, sulfuric acid is a strong diprotic acid, so the concentration of hydrogen ions will be equal to twice that of the concentration of the acid. The next step is to write out the equation linking the concentration of hydrogen ions with pH. So the concentration of hydrogen ions equals 10 to the minus pH. We'll then need to sub in the value of pH to calculate the concentration. Now we've got the concentration of hydrogen ions, we need to work out the concentration of the acid. So we know from looking at the equation that the concentration of hydrogen ions is equal to twice that of the acid. So by rearranging this equation, we can calculate the concentration of the acid. Now we've rearranged the equation, all we need to do is sub in the concentration of hydrogen ions we worked out earlier. And this gives us a final answer of 0.025 moles per decimeter cubed. Sometimes you need to work out how the pH changes when the volume of the solution changes, so when it's been diluted by adding water. The following equation shows you how to do that. So to work out the new concentration of hydrogen ions, you do your original concentration times by the original volume divided by the new volume. Now you can generate this equation just by using moles equals concentration times volume. So let's say that M1, so the rest of the equation, the M1, the C1 and the V1, represent your new moles concentration and volume, and the 2's for the second equation represent the original concentration and volume. Now, if we're adding water to a sample of the acid, it's not going to change the number of moles of acid there, because we're not adding or removing any acid, and we're not doing a reaction with the acid. Therefore, the moles for both sets of equations will be the same. This means we can set both equations as being equal to each other. So the new concentration times the new volume will equal the original concentration times the original volume. By rearranging this equation, you'll see it matches the one that I've written at the top. This proof can be useful in case you forget the equation at the top. You can always work out how to do your dilution by using the first principles of moles equals concentration times volume. For this worked example, we're calculating the pH of the solution formed when 1000 centimeters cubed of water is added to 500 centimeters cubed of 0.1 moles per decimeter cubed of hydrochloric acid. To start off this question, we need to write down the two equations we need to answer it. So we need to write down the equation showing us how to work out the new concentration when we've done a dilution, and the equation linking the pH and the concentration of hydrogen ions. Once we've written these down, The next step is to sub in the values to the dilution equation to figure out what our new concentration of H plus is going to be. It's worth remembering that the new volume is the combined total of both volumes. It's not just the amount you've added, it's the total of both. Sometimes a question will say, calculate the pH formed when a 1000 centimetre cubed solution is made up to a 2000 centimetre cubed solution. In that case, your new volume will be 2000 centimetres cubed. Just be careful to make sure you read the question really carefully. So this gives us a new hydrogen ion concentration of 0.03 recurring. We can then sub this into the pH equation. And once we put it in, we just need to enter it into our calculator, making sure to give our answer to 2 decimal places. Kw is the ionic product of water. Now, we use this for the pH calculations of strong bases. I'm going to show you how we come to arrive at what Kw is. So water will dissociate into hydroxonium and hydroxide ions. And this is how it's represented. It's an equilibrium process. Now if we write out the equation like this, what we can then do is cancel off a water from each side. So we can remove one of the H2O's from the left, and we can remove one of the H2O's from the right. It will give us this equation. Now this is an equation you'll have seen before. Water in an equilibrium with an H plus ion and an OH minus ion. But it's actually a simplification of those two equations I've written above. So it represents the fact that two water molecules actually form a hydroxonium ion and a hydroxide ion. Because from the work we've done earlier in the topic, we know that when an acid reacts with water, it will form that hydroxonium ion. So we don't always have these H plus ions free in solution. But this is a common simplification. So I've rewritten this at the top, and we can now apply the equilibrium law to this equation. So what you've already covered earlier in the course. So we've just turned it into one of those Kc equations. Now water only dissociates a tiny amount, so the equilibrium will lie so far to the left, we can consider the amount of water to be constant. Given that we consider the amount of water to be a constant in this equation, we can rewrite it as follows. To help us simplify this equation, in chemistry we say that Kw is equal to the Kc times the concentration of H2O. This means we can say that Kw is the concentration of hydrogen ions times the concentration of hydroxide ions. Because we can see that the Kc times H2O is equal to the H plus and OH minus concentrations. So why do we need to know what Kw is? Well, Kw is a constant. It will always have the same value for an aqueous solution at a given temperature. So, for example, at room temperature, Kw equals 1 times 10 to the minus 14. Now this is important because it means if we write the Kw equation again, we can therefore say that 1 times 10 to the minus 14 equals the concentration of hydrogen times the concentration of hydroxide ions. In pure water, the concentration of hydrogen equals the concentration of hydroxide, which means we can therefore say that the ionic product of water is equal to the concentration of hydrogen squared. And we'll use some of these key features when we're working out the pHs of strong bases. So a strong base will fully ionise in water. So for example, sodium hydroxide will dissociate into the sodium ion and the hydroxide ion. So since 1 mole of the base equals 1 mole of hydroxide ions, we can say that the concentration of hydroxide will be equal to the concentration of the base. Now if we calculated the concentration of an acid, we would go straight into our pH and H+ equations. But all pH calculations involve the use of H+. There's no pH calculation taking into account the concentration of OH-, because remember, pH is a measure of the concentration of hydrogen ions. So this is where we can bring in the Kw equation we looked at a moment ago. This now gives us an equation linking the concentration of hydrogen ions to the concentration of hydroxide ions. We can work out the concentration of hydroxide ions from the concentration of the base. Kw is a constant, so for example at room temperature it's 1 times 10 to the minus 14. So therefore we can calculate the concentration of H+, and then just use it in the equations like we have done over the previous few examples. So let's look at this in practice. We've been asked to find the pH of a 0.2 mole per decimeter cubed sample of sodium hydroxide, and we're given the value of Kw. The first thing we need to do is write down all relevant equations for this question. So we're going to need to write down the equation of what Kw is, and then how can we calculate the pH. So these are the two key equations we need for this question. We then need to work out the concentration of the hydroxide ions. Well, we know that sodium hydroxide is a strong base, so therefore the concentration of the hydroxide ions will be equal to the concentration of the base. So therefore the concentration of hydroxide ions is 0.2 moles per decimeter cubed. We now need to convert that concentration of hydroxide ions into a concentration of hydrogen ions. To do that, we'll need to rearrange the Kw equation. So we need to rearrange the Kw equation to make the concentration of hydrogen ions the subject. And this is the rearranged equation. So the concentration of hydrogen ions equals Kw divided by the concentration of OH-. The next step is to stub in the values. So we know the concentration of hydroxide. We are given the value of Kw. So we can now calculate the concentration of hydrogen ions. Now we've worked out the concentration of hydrogen ions, all that's left is to put that concentration into our pH equation. Once we've subbed that in, we'll put it into our calculator, making sure to give our answer to 2 decimal places. So the final answer is a pH of 13.30. We're now going to look at the acid dissociation constant, Ka. Weak acids will only partially dissociate, so it's not quite as straightforward to calculate the pH as it is for strong acids. As we looked at earlier, for a general acid, a weak acid, it will be in equilibrium with the A- ion and the H+ ion. Now the equilibrium will lie quite far to the left, so therefore the concentration of the acid doesn't equal the concentration of hydrogen ions. So in order to work out the concentration of hydrogen ions, we're going to have to use the acid dissociation constant. And this is a bit like a special case of Kc, like we looked at earlier in the course. So we can rewrite the equilibrium of HA being in equilibrium with the A- and the H+, as Ka equals H plus A- over HA. So we've rewritten this equilibrium out, so we've got a bit more space. And we now need to consider what the concentrations of the H+, the A-, and the HA are. Now, weak acids only dissociate a tiny amount, so therefore the concentration of the undissociated acid, HA, is going to be a lot higher than the concentration of the hydrogen ions. This means we can say that the concentration of the undissociated acid at the start is going to be equivalent to that of the undissociated acid at equilibrium. Now, it's an assumption we're making because obviously the concentration will change, but it's only changing by such a small amount. We assume that the concentration of the acid at the start is equal to that of the concentration of the acid in equilibrium. Now, since all of the H+ in our sample comes from the acid, so it comes from the HA, we can assume that the concentrations of the H+ and the A- are the same. So we're not getting the H+ from any other source other than the acid. So again, it's another assumption we can make. This is important for two reasons. The first one is that we only are given the concentration of the acid at the start. We don't know what the concentration of the acid is at equilibrium. However, we assume that it's the same. So we can use the value of the acid at the start, the concentration of the acid at the start, as the concentration of the acid in equilibrium. So we can work out, or we can be given, what the concentration of the acid is. Now, since all of the H+ comes from the HA, so we've said that H+ is equal to A-, we can make a further simplification. Therefore, the acid dissociation constant equals the concentration of hydrogen ions squared divided by the concentration of the acid. Just like with Kw, Ka is a constant, so it'll be given to you in the question. The concentration of the acid will usually be given in the question as well, which means you can then rearrange the equation to work out the concentration of the hydrogen ions. For this worked example, we're finding the pH of a 0.01 mole per decimeter cube solution of ethanoic acid. The Ka of the ethanoic acid is given as 1.5 times 10 to the minus 5. The first thing we need to do to answer this question is to write out the Ka equation, so the equilibrium equation. So we can say that Ka equals the concentration of hydrogen ions times the concentration of the ethanoate ion divided by the concentration of ethanoic acid. We can then use a simplification we looked at a moment ago to rewrite this equation. Now we've simplified this, in the question we're given the concentration of the ethanoic acid and we're given the value of Ka. So if we rearrange this equation to make the concentration of hydrogen ions the subject, we'll be able to sub in the values and work out the answer. So our rearranged equation is the concentration of hydrogen ions is equal to the square root of the Ka times the concentration of the acid. So remember, everything inside those brackets is being square rooted. What we need to do now is sub the values from the question into the equation. And once we've subbed these values in, we just need to put them into our calculator to give us a concentration of hydrogen. So the concentration of hydrogen is 3.87 times 10 to the minus 4. The next step will be to sub this into the pH equation. It's important to remember here that these answers are often quite long numbers in your calculator. It's really important that when you're working through a question like this, you use the answer button rather than rounding too early. If you were to put this rounded answer into the next step, your final answer would be different from that I've got on the screen. So make sure you press the answer button to copy the whole number through to the next step. So once we've subbed our values in, all that remains is to put this into the calculator and make sure to give our answer to 2 decimal places. So the final answer is a pH of 3.41. So in this question, we're told that the pH of an ethanoic acid solution is 3.27 at 298 Kelvin. We need to calculate the concentration of this solution. The Ka of ethanoic acid is 1.75 times 10 to the minus 5 at 298 Kelvin. Now, the reason we're given the temperatures is this is an equilibrium constant. So the Ka is that value at that specific temperature. It means they've got to tell us what the pH is at that temperature as well. However, the temperature isn't involved in the equation, we don't need to do anything with it. It's just extra information that you have to be given in the question. The first step to answering this is to write out the equation linking the H plus concentration with the pH. We then need to sub in the pH that we're given in the question, and then put this in the calculator to give us a concentration. So our concentration of H plus is 5.37 times 10 to the minus 4. And again, remember, I've rounded this answer so I can write it on the screen. You'll need to use the answer button in your calculator between all of these stages. The next step is to write out the Ka equation, and we can then use the simplified version of it as well. Now we've got our simplified equation, we need to rearrange it to make the concentration of ethanoic acid the subject of the equation. We can now sub in the value of Ka that we were given in the question, add in the value of H plus which we've calculated, and then put this in our calculator to give us our final answer. So the solution to this question is a concentration of 0.016. So for this question, a solution of 1.75 moles per decimeter cubed ethanoic acid has a pH of 3.5. What is the value of Ka? So we're going to need to start off by writing down the equation linking the pH to the H plus concentration. Once we've done this, we can sub in the values from the question, and then put it in our calculator to get a final answer. Once we've written this, we can construct the Ka equation and then use the simplification. In this case, the question is asking us to work out the acid dissociation constant, so there's no need to rearrange it. We can just sub the values that we've worked out and from the question straight in. Once we've subbed the values in, we just need to put it into our calculator. So the final answer is 5.71 times 10 to the minus 7. It's really important that you show all the steps in your workings out. Don't just sub the values in without writing down what calculation you're actually doing. That way, if you make a mistake, it can be spotted. Now, because Ka is calculated from the hydrogen ion concentration, or the pH, and we know that's calculated itself from an equation involving logs, the value of Ka can vary massively. So instead, we use a logarithmic constant, pKa. So in order to calculate pKa, you do minus log to the base 10 of Ka, and the reverse to calculate Ka, from pKa you do Ka equals 10 to the power of minus pKa. Now you'll notice these equations are very similar to the pH and the H plus equations. So that can be a quick way to remember them if you forget. You can see that pKa is analogous to the pH equation. So let's look at a pretty straightforward example. If an acid has a Ka value of 2.5 times 10 to the minus 7, what would the pKa be? Well, the first thing we need to do is write down the equation linking pKa and Ka. Then we just need to sub in the values. And finally, work out the answer using our calculator. Giving us a final answer of 6.60. So we can see how we've gone from a Ka of 2.5 times 10 to the minus 7 to a pK of 6.6. And most pKa's come in a similar range to those of pHs, so the numbers aren't going to vary massively. It's why we typically use pKa over Ka in chemistry. So for this example, we're told if an acid has a pKa value of 3.615, calculate the Ka value. So the first thing we need to do is write down the equation linking pKa and Ka. Once we've done that, we then need to sub in the values from the question. And then finally, use our calculator to get the answer, which in this case is 2.34 times 10 to the minus 4. This is a bit of a longer worked example, so we've been asked to calculate the pH of a 0.15 mole per decimeter cube sample of ethanoic acid. Ethanoic acid has a pKa of 3.75. So in this case, we're going to do pretty much the same thing we've done before when we're working at the pH of a weak acid. But this time, rather than being given the Ka value, we're given the pKa. So once we've converted the pKa to a Ka value, it's the same thing that we've looked at earlier in the video. Now we're quite confident with how to change Ka and pKa into each other, and we're not going to write down the equation to start off with. So Ka equals 10 to the power of minus pKa, so Ka equals 10 to the power of minus 3.750. Once we put this into our calculator, we get an answer of 1.78 times 10 to the minus 4. The next step is to write out the Ka equation for ethanoic acid, and we can add in the simplified version of it as well. So the Ka will equal the concentration of the H plus times the concentration of the ethanoate divided by the concentration of the acid, and we know we can simplify this to the concentration of the H plus squared divided by the concentration of the acid. Now all that's left to do is to rearrange the equation to give us H plus and then sub in the values. So we've rearranged the equation, again noting that the square root is for everything inside the brackets, so we're square rooting Ka times the concentration of the bracket. And once we've subbed our values in, we just need to put this into our calculator. Giving us a hydrogen ion concentration of 5.16 times 10 to the minus 3. As usual, please make sure that you use the answer button on your calculator to copy this through to the next step. So we now need to write the equation linking H plus and pH together and sub in the value for the H plus which we've worked out here. So all that's left to do is to put this into our calculator and then make sure we give our answer to 2 decimal places. Giving us a final pH of 2.29. A titration curve shows the result of a titration practical. So you plot the pH against the amount of base added, if we're starting with an acid, Obviously, if it was the other way around, you'd plot the volume of acid added. So this is what the graph would look like. You've got the pH going up the left-hand side, and you've got the volume of base added along the bottom. Now, there are 4 examples we're going to look at. The first is what happens when you titrate a strong base against a strong acid. So we're starting with the strong acid in the conical flask, and we're adding the base to it. We can see that as we have the acid in the flask initially, the pH is quite low to start off with. As the volume of base increases, there might be a slight change in the pH. We then get quite a rapid change in the pH for a very small amount of base, and then a levelling off at the pH of the base. This vertical section is called the equivalence point, or the end point. At this point, a tiny amount of base will cause a large pH change. So it's at this point here where all the acid is neutralised. So whatever volume here, all the acid will have been neutralised. It's not a linear curve, the pH doesn't gradually change as it's added. All of a sudden you get quite a rapid change at the equivalence point, or the end point. This is the curve when we start with a strong acid and we add a weak base to it. Again, the pH starts off quite low because we've got a strong acid. However, the curve doesn't quite go up to a higher pH because we've got a weak base rather than a strong one in the last example. Next, we have the curve for a weak acid against a strong base. So the initial pH is a bit higher this time because it's a weak acid rather than a strong one. Again, we still have an end and equivalence point, and we end up at the high pH of the strong base. Finally, we have the graph for when we use a weak acid and a weak base. Now this curve is less well defined. You don't see the same kind of vertical end or equivalence point as you do when you use a strong acid or a strong base. It's very difficult to see the end point when you have a weak acid, weak base titration. If you were to use an indicator, for example, the colour change would be gradual, making it very difficult to see the end point. If you were using a weak acid and weak base, like we are in this case, you'd normally use a pH probe to measure the pH, rather than using an indicator. When you do use an indicator in a titration, to see where the end point is, it's important to make sure that the indicator you pick changes colour throughout the end point of the titration. You need to pick one which changes colour in a narrow pH range, and that pH range has to be completely within the vertical section of the graph. So it has to change in this region here. So let's say we were wanting to do this titration, and we were given a choice of 2 indicators. Indicator A, where its pH range for its colour change is 3 to 4.5, and indicator B, which has a pH range for its colour change of 8 to 10. Well, the indicator which would be suitable would be indicator A, because indicator A would change colour between pH 3, which is about here, and pH 4.5 about here. If we use indicator B, while it would be pH 8 here, the 10 is outside of the equivalence point range, so that indicator wouldn't be any good. So, for example, if we were using indicator A again, we start off well below pH 3. This means it'll be its first colour when it's in the acid. During the equivalence point here, the range for the colour change takes place, and then it'll be its second colour when it reaches the end point. You covered titration calculations right at the start of your physical chemistry course. However, they can be asked again in this acids and bases topic, so we're going to quickly recap how you go about answering titration calculation questions. The first step is to write a balanced equation for the problem you're given. You may be given this, or you may have to write it by yourself. The next thing you need to do is to read the question carefully and determine what information you've been given, what concentrations have you been given, and what volumes have you been given. You can then decide what other information you're going to need to work out using the information you've been given. It's always then a good place to start by calculating the moles from the known values. So in the question, you'll be given the concentration and a volume of the acid or the base, so you can work out what the moles of that acid or base are. The next step is to use the molar ratios from your balanced symbol equation to work out how the moles of the acid correspond with the moles of acid of the base. It could be a 1-to-1 relationship, or you might have to times or divide your moles by 2. We'll look at a worked example of this in a minute. The final step is to calculate the unknown values, so to finish off the question. This question asks us to use the titration curve, which shows the results when 0.75 moles per decimeter cubed of sodium hydroxide was titrated against 45 centimeters cubed of hydrochloric acid. We need to calculate the concentration of the hydrochloric acid solution. Unlike some titration questions you might have seen, this one doesn't tell you what volume of sodium hydroxide was used. You need to read the value from the graph. So the volume at which neutralisation occurred is the volume at the end of the equivalence point. So you've got to read that value off the graph. So we can see that the volume of sodium hydroxide added when neutralisation was occurred was 20 centimeters cubed. So we're now going to follow the first step, which involves writing down the equation. So this is a pretty straightforward equation of hydrochloric acid reacting with sodium hydroxide to produce sodium chloride and water. The next step is to look at the question and write down all of the key bits of information. The value of the concentration of sodium hydroxide was given in the question, as was the volume of hydrochloric acid. The volume of sodium hydroxide we read off the titration curve. The next step is to convert the two volumes from centimeters cubed to decimeters cubed. We do this now to save time later on, and we do this by dividing each value by 1000. Now we've got the volumes in decimeters cubed, we can start by working out the moles of the known one. So we've got 2 bits of information for sodium hydroxide, so we need to start by working out how many moles of sodium hydroxide we've got. We do this by using the equation moles equals concentration times volume, so we can now sub in the values for sodium hydroxide. So we then put these into the calculator to get an answer. So we know we have 0.015 moles of sodium hydroxide. Since there is a 1-to-1 ratio of the hydrochloric acid to the sodium hydroxide, this means we must also have 0.015 moles of hydrochloric acid. Now we know how many moles of hydrochloric acid we have, we can use our moles equals concentration times volume equation to figure out what the concentration of the hydrochloric acid must be. So we'll rearrange that equation, so concentration equals moles over volume. Now we need to sub in the values for the moles of hydrochloric acid and the volume of it. Now all we need to do is once again put this into the calculator to get a final answer. So the answer to this worked example is 0.3 recurring moles per decimeter cubed. The titration curves are a little bit different for diprotic acids. Just to recap, a diprotic acid is one which releases 2 protons. However, these protons are removed separately. There are 2 stages. So for example, let's look at the titration curve of sulfuric acid. You can see that this titration curve has 2 distinct equivalence points. Each of the protons are removed separately. So the first equivalence point represents the loss of the first hydrogen ion, and the second equivalence point represents the loss of the second hydrogen ion. Let's look at what happens when ethanoic acid is deprotonated. So when this acid with two carboxylic acid groups react with a molecule of base, it's going to lose one of the H pluses, which we can see here, and this will be represented by the first equivalence point on the titration curve. We can then lose a second H plus, which is represented by the second equivalence point. We're now going to look at the worked example for a titration of a diprotic acid. So a 20 centimetre cubed sample of sulfuric acid was completely neutralised by 30 centimetres cubed of 0.25 moles per decimetre cubed sodium hydroxide solution. We need to calculate the concentration of the sulfuric acid. So the first thing we're going to do is write out a balanced symbol equation for this. Once we've written the symbol equation, the next thing we need to do is extract all of the key information from the question. So from reading the question, we can see that the volume of sulfuric acid is 20 centimetres cubed, the volume of sodium hydroxide is 30 centimetres cubed, and the concentration of sodium hydroxide is 0.25 moles per decimetre cubed. What we need to do now is change the two volumes from centimetres cubed to decimetres cubed. And again, we do this by dividing by 1,000, and this saves us work or saves us forgetting later on in the question. Now that we've converted the volumes from centimetres cubed to decimetres cubed, we can work out the moles of sodium hydroxide. So we'll use the moles equals concentration times volume equation. Once we put this into our calculator, we should get an answer of 7.5 times 10 to the minus 3. So as we can see from the equation, 2 moles of sodium hydroxide are needed to neutralise 1 mole of sulfuric acid. So we need to take this ratio into account when determining how many moles of sulfuric acid we've got. So because of that ratio, we need to divide the moles of sodium hydroxide by 2, because there are 2 lots of sodium hydroxide for every 1 lot of sulfuric acid. So the moles of sulfuric acid will equal 7.5 times 10 to the minus 3 divided by 2. Now we've got the moles of sulfuric acid, we can use moles equals concentration times volume one more time to work out the concentration of sulfuric acid. We're now moving on to the final part of this topic, which is looking at what buffers are. So a buffer is a solution which causes another solution to resist changes in pH when a small amount of acid or base is added. There will still be a very, very small change in the pH, but it keeps the pH roughly the same. Now, we find buffers in things like hair shampoo. Alkaline conditions makes hair feel rough, so by using the buffer to keep the hair at a slightly acidic pH, hair feels smoother. We also find buffers in the body. So the body has natural buffers inside of them, so where enzymes have an optimum pH range, they stay within that range. The body's pH is regulated through the use of buffers. There are 2 types of buffers, acidic buffers and basic buffers. We're going to start off by looking at what an acidic buffer is. So an acidic buffer is a mixture of a weak acid with one of its salts. So we're going to look at an example of one of these. So ethanoic acid is a weak acid. It partially dissociates. So if we had a solution of ethanoic acid, the mixture of the weak acid, the vast majority of this mixture is going to be the ethanoic acid here. We're only going to have a very small amount of what's on the right hand side. However, to that mixture of the weak acid, we also add one of the salts of the weak acid. So for example, sodium ethanoate is the salt of ethanoic acid. Because this is a salt, it will fully dissociate. So when we add the salt of the weak acid, we add a large concentration, effectively, of this negative ion here. This means that the buffer solution contains large amounts of both the ethanoic acid, because the majority of the ethanoic acid comes from the ethanoic acid we've added, and from the negative ion from its salt, and this comes from adding the salt here. So this is our buffer solution. We've got a very large amount of ethanoic acid in the buffer, and we've also got a very large amount of the ethanoate ion in the buffer. We're now going to look at how this buffer resists the pH change when acid is added and when a base is added. So if we add an acid, we're increasing the concentration of the hydrogen ions. If we increase the concentration of the hydrogen ions, the equilibrium will shift to oppose that change. In order to oppose that change, the equilibrium will shift to the left. So what we're causing to happen is the ethanoate ions, which there are lots of, to react with any H plus added, to reforming the ethanoic acid. So any additional H pluses which are added are then removed, so the pH stays constant. If we add base, the hydroxide ions will react with the H plus ions in solution to make water. This is going to reduce the concentration of hydrogen ions in the solution. If we decrease the amount of hydrogen ions in the solution, the equilibrium is going to shift right to replace the lost hydrogen ions, therefore replacing them and keeping the pH constant. It causes this reaction to happen here. So all of the ethanoic acid we've got will now dissociate into the ethanoate ion and the hydrogen ion. So similar to an acidic buffer, a basic buffer is a mixture of a weak base with one of its salts. Some of the base will react with water. So some of our base here, our ammonia in this case, will produce the NH4 plus and the OH minus. But just like the acid, the equilibrium shifts far to the left, so it doesn't really dissociate. So when we add the weak base, the vast majority of that solution will be the weak base. We're also going to add the salt of the weak base. So if we add ammonium chloride to the solution, that's going to dissociate, giving us a high concentration of the ammonium ions in the solution. This means that the buffer solution will contain large amounts of both the weak base and of the salt, as we've added the salt, which will give us a high concentration of NH4+. So we're now going to look at how basic buffers resist the pH change when an acid or alkali is added. Again, remember this buffer is going to have large amounts of the weak base and large amounts of its salt. When acid is added to a basic buffer, the H plus added will react with the OH minus. This is going to form water. So this means the equilibrium is going to shift to the right because we're losing OH minus from this solution. So if we decrease the amount of OH, because it's reacted with the added acid, the equilibrium is going to shift to the right. So this reaction will happen. The NH3 we've got in the solution will react with the water to form the NH4 plus and the OH minus. So any H plus which has been added to the solution is effectively mopped up by the OH minus and the pH won't change. If we add a base to a basic buffer, this will increase the concentration of OH minus. This will cause equilibrium to shift to the left to reduce the concentration of OH minus. Therefore, this reaction will be happening. The high concentration of NH4 plus we've got will react with the added OH-, forming NH3 and H2O, keeping the pH the same. If a small amount of water is added to a buffer solution, the pH will still stay constant. This is because in pure water, the concentration of H+ equals the concentration of OH-. Now we've seen in these few examples how if we add either of these to a buffer solution, the pH remains constant through the change in equilibrium. If we add both H+ and OH- in equal amounts, like in pure water, it's going to push the equilibrium in equal ways in opposite directions, so there'll be no change overall. So diluting a buffer by a small amount will not affect the pH. We're now going to look at the steps involved in calculating the pH of a given buffer solution. The first step is to write out the Ka equation for the weak acid. Once you've written out your Ka equation, you then rearrange to make the concentration of hydrogen the subject, sub in the values from the question, and solve it. Once you've determined the concentration of hydrogen ions, you can then apply it to the pH equation and come out with your pH value. We're going to look at a worked example of this. So this question asks, a buffer solution contains 0.5 moles per decimeter cubed of ethanoic acid and 0.7 moles per decimeter cubed sodium ethanoate. For ethanoic acid, the Ka equals 1.74 times 10 to the minus 5. What is the pH of this buffer? Well, the first thing we need to do is write the Ka equation. So let's start off by writing the equilibrium. Once we've written the equilibrium of the buffer solution, we can now turn this into the Ka equation for the weak acid. And we should be quite familiar with writing Ka equations now. We're now going to look at how we can work out what the concentration of each of these are. So just like with Ka, we make a couple of assumptions when doing buffer calculations. We assume that at equilibrium, the concentration of the negative ion is equivalent to the concentration of the salt that we added. And that's because the weak acid doesn't really dissociate into its salt. So we can assume that all of the negative ion comes from whatever salt we chose to add to it. Likewise, because that weak acid doesn't really dissociate, we can assume that the concentration of the weak acid at equilibrium is the same as the concentration of the weak acid at the start. So what we can now do is sub these values into the equation and rearrange the equation to give us the concentration of hydrogen. So this is our rearranged equation. We've subbed in the values we were given in the question, so we'll now put this into our calculator. And the concentration of H+ comes out at 1.24 times 10 to the minus 5. Again, it's important to remember that you need to use the answer button on your calculator here, otherwise you're going to end up with a rounding error. And as we've seen now many times throughout this topic, once we have a concentration of H+, we can use pH equals minus log to the base 10 of that H+ concentration, giving us a final answer of 4.91. Again, we're making sure to round our answer to 2 decimal places. There is another way we can make acidic buffers though. We can add a weak acid to a small amount of an alkali. Now this produces a small amount of the salt of the weak acid, therefore producing an acidic buffer. So for example, if we reacted ethanoic acid with a small amount of sodium hydroxide, we would produce some sodium ethanoate and water. However, we would still have some of the ethanoic acid left over. So what we're going to do now is we're going to look at an example and see if we can work out how many moles of each will be left over. So we're going to look at the moles at the start of this reaction, how they change during the reaction, and the moles left over at the end. So let's just assume that in this reaction we're reacting 10 moles of ethanoic acid with 2 moles of sodium hydroxide. Now obviously at the start of this reaction we don't have any moles of product yet. In this reaction, all of the sodium hydroxide is going to react with the ethanoic acid. So this means all the sodium hydroxide will be used up, we've lost 2 moles of it, and it's going to react in total with 2 moles of the ethanoic acid. So we'll use up 2 moles of that ethanoic acid. Given the ratios of all products are 1 to 1 to 1, this means that we're going to produce 2 moles of the ethanoate salt and 2 moles of water. If we then compare the moles we had at the start with how those have changed, we can work out how many moles are left. So therefore we can see that by doing this reaction, we've got a solution of the weak acid with some of its salt. There's none of the base left over, so the base is no longer in solution. It can't interact with any acid or base added, which is why the buffer solution is still just the weak acid and its salt. There are a few additional steps though if you need to calculate the pH of a buffer solution made this way. The first thing you need to do is write out an equation. So that's going to be your acid and base reacting together to produce salt and water. You then need to calculate the moles of everything at the start, calculate how those moles change through the reaction, and that will give you a value for the moles at the end of the reaction. Once you've got the moles of the acid and the salt, you can then calculate the concentration of the acid and the salt using your new volume, which will be the total volume, so it's the volume of the acid added to the volume of the base that you used. Then you'll just calculate the pH like you would do for a normal buffer, so like the example we looked at a few minutes ago. For this worked example, we're asked, a buffer is formed by mixing 50 centimeters cubed of 0.8 moles per decimeter cubed sodium hydroxide and 100 centimeters cubed of 1 mole per decimeter cubed ethanoic acid. We need to calculate the pH of this buffer solution. So we're going to start off by writing an equation out. Now we've written the equation out, we need to look at what's happening to the moles at the start, how they're changing, and at the end. Now the question doesn't give us the moles of these, instead it gives us the volume and concentration of the sodium hydroxide and of the ethanoic acid. So we're going to have to work out the moles of each using moles equals concentration times volume. So these are the two calculations we would need to do to calculate the moles of each of them. So we'd need to use the concentration of ethanoic acid times the volume of it, and the concentration of sodium hydroxide times the volume of it. So that will give us 0.1 moles of ethanoic acid and 0.04 moles of sodium hydroxide. So we can now add these underneath the equation we've written. During the reaction, all 0.04 moles of sodium hydroxide will react with the 0.1 moles of ethanoic acid. So that means the moles of each of these will decrease by 0.04. It's a 1 to 1 to 1 to 1 ratio of reactants and products, so we're going to produce 0.04 moles of the ethanoate salt and of water. This means the moles at the end of this reaction are as follows. So we have in our buffer solution 0.06 moles of ethanoic acid, no sodium hydroxide left, 0.04 moles of the sodium ethanoate salt, and 0.04 moles of water. What we can do now is work out the concentration of the acid and the concentration of the ethanoate salt. In order to calculate these, we'll need to know what the total volume of the solution is. So in this reaction, we added 50 centimeters cubed of hydroxide to 100 centimeters cubed of acid. This gives us a new total volume of 150 centimeters cubed, which will convert straight away to 0.15 decimeters cubed. We can now use a rearranged moles equals concentration times volume equation, so the concentration equals the moles divided by the volume, to work out the concentration of the ethanoic acid. We'll do exactly the same process for the ethanoate salt. Giving overall concentrations of 0.4 moles per decimeter cubed for the acid and 0.26 recurring moles per decimeter cubed for the salt. I've rewritten them up here to give us a bit more space. Now, we've done the tricky part of this buffer calculation. All that's left is to treat it as a normal buffer question, so we now need to write the Ka equation. Once we've written the Ka equation, we need to rearrange it to find the concentration of H+. Now all we need to do is substitute the values in and put it into our calculator. So this is the equation with the values subbed in. And the value of the concentration of the hydrogen ions is 2.61 times 10 to the minus 5 moles per decimeter cubed. We now need to put this into our pH equation. Therefore giving us a final answer of a pH of 4.58.